And there's his title, so let's enjoy.
Okay. Let us start. First of all, I have to thank to the Institute and to the organizer of the program for possibility, for kind invitation, and possibility to give a talk on this meeting. Okay, but let us start. The topics of the talk is the theory of nonlinear hydroelastic waves. This waves was discussed last day very thoroughly through the day, therefore I don't need to explain what is it. But we are focused on the global. First, I am sorry, it will be mathematical talk, and with some statement, lemma or something, theorem. And second, our consideration are based on the variational principle, therefore no dissipation energy or something like this, pure variational problem, and I try to develop some mathematical tools for solving of this problem. In fact, it is this work starts 9 or 10 years ago. It is in fact joint work with John Toland, but it takes a time to understand how the thing is running, and now I try to present maybe some preliminary results. Okay, let us continue. A few words about title. We consider the conformal geometry deals with geometric objects which are invariant with respect to conformal mappings. Conformal transforms. Conformal transforms in multidimensional space, it is not too many. You can list it all. It is different translation, rotation, and maybe inversion. Therefore, and different composition of such a mapping. Therefore, it is very, very poor set. And the geometric quantities which are invariant with respect to conformal transform on the ambient space, usually it is subject of study of conformal geometry. It turns out that these questions are related to the problem of hydroelasticity, and we will see below. Okay? It is written what is we try to do. Really, we will try to develop some approach based on the variational principle to global problem of hydroelastic waves, and then to get something maybe preliminary, maybe not so good result. We are focused on the problem of periodic traveling waves, but three-dimensional, in 3 dimensions. Okay. Since our approach is based on the variational principle on the energy, it will be better to start from the discussion what the total energy of hydroelastic flow, how it can be written, and what is it. Okay. First about general picture, how we assume that the shell or sheet, elastic sheet, it is some periodic surface with periods equal to 1 for simplicity. Therefore, it is invariant with respect to translation. And it is a boundary of some domains in 3-dimensional space. These domains also should be invariant with respect to translation. Here, I, J, K are the standard canonical bases in R3. Okay, this is picture maybe say more. You have something like hydroelastic shell and water under this shell, and this is space variables X. One thing that may be unusual, I supply coordinate with superscripts upper indexes because it is in geometry, it is so-called contravariant variables, and the indexes should be above X. No problem. Okay. About the liquid, it is assumed the flow is rotational, incompressible, also satisfies periodicity condition. It is not so good because yes, no, it's correct. This periodicity condition and satisfies Neumann condition, non-permeability condition on the free surface, and tends to unit vector, uniform flow as x3, vertical coordinates tends to minus infinity. Therefore, we are in a moving frame, water is moving, surface is standing. Okay, next. Under this assumption, we can introduce the flow potential. It will be satisfy the standard equations. It is harmonic function. It can be represented in this form. Here, capital phi is the periodic harmonic potential, and this is a Neumann condition, and this condition at minus infinity. I know that the pressure is given by this formula because of Bernoulli law, and this constant may be taken to zero without loss of generality. Okay, I denote by omega and by sigma the intersection of the surface and domain with the cell of periods because we can focus only on period. And first about energy of liquid, kinetic energy of liquid. In this, real kinetic energy is infinite because we have an infinite depth and the velocity tends to do not tend to zero at infinity. It is so-called renormalized or reduced kinetic energy. It is all stuff. Roughly speaking, the kinetic energy in the, if you have finite depth, kinetic energy is equal to this expression, but plus some constant, unessential. These constants tend to infinity when the depths tend to be minus infinity to infinity. Then if we remove this constant, it is some absolute constant, we come to this expression. Okay, therefore we can consider this quantity like some renormalized. It is bounded. Okay. Next, the gravity energy, the same, we have to apply the same procedure to the gravity energy of the, because it is really infinite for infinite domain. And then we get some expression. It is will be reduced gravity energy. It is more or less known things, and it is simple. Next, let us discuss the elasticity theory. Let us discuss the elasticity theory. This stuff becomes more complicated because for nonlinear elasticity there is many approaches how to model elastic sheet and energy of elastic sheet. And therefore we can mainly two approach. One is based on the asymptotic analysis. We can some three-dimensional plates, then take the thickness of the plate tends to zero. We find so-called gamma limit. It will be the energy of the elastic shell. And the other is the Cassera theory, which considers the shell as two-dimensional continuum, but supplies it with some vector of director. In our case, it is, I try to choose the frame such that this theory almost coincides. Therefore, I base it on the first approach. Yes. It is rigorous result by Frieseke, James and Muller, that after this passage to the limit, the bending energy may be written in the form. Here A is A, capital A in bold. It is the second fundamental form of the surface. Not necessary to know what is it, but later I try to say about this. The most important that the invariant of this form, the second invariant, is sum of the principal curvatures and the trace of A, which is like mean curvature. Yes, it is a remarkable fact that this result don't depend on the physical or geometric nonlinearity of the material, because we start with some nonlinear material. All properties of this linear material are focused in this constant. You can calculate it directly if you know the stored elastic energy of nonlinear material. It is a very nice result. Therefore, I have some little bit comment. By the Gauss-Bonnet theorem, maybe somebody remember what does it mean, the Gaussian curvature K1 multiplied by K2 is some kind of topological invariant, and the integral of this depends only on the topological type of this surface. In our case, it is topological torus. For torus, it is equal to pi multiplied by Euler characteristics, which is topological invariant. For torus, it is simply 0. Therefore, we can the equation for bending energy simplify. It is equal to this stuff, and it is equal to this integral. This integral is very special. It is named Wilmorm function of the surface sigma. It is conformal invariant. This is the reason that we deal with conformal geometry. Okay. Okay, for membrane energy, it is a difficult question. For energy of stranges. The asymptotic analysis, rigorous asymptotic analysis, was made by Lavrentyev and Rowe. And answer is very complicated. Even the nonlinear energy of elastic shell is not good function like U, because something very good function. The expression for the energy of membrane or stretching energy may be very complicated. Even non-smooth function includes very strange results, in contrast to the bending energy. I take simplistic case on the linear elasticity. If, for example, X, so our surface X has some parameterization, some abstract surface, then the membrane energy follows Lavrentyev and Rowe, should be written in this, where J is the first fundamental form of the surface, or metric tensor of the surface. It is not so bad. However, there is one thing which we have to focus on. When we start our work with John, and John asked very question which looks like very simple, but really is not. Suppose I have, where is this picture? Yes. Suppose I have some photo of picture of the elastic shell. It is easy to calculate the bending stresses because they are simply curvatures. It is clear. But can we say, is it stretched or not? Looking at this picture. The answer yes and no. Because, for example, if it is a flat surface, it may be stretched or not stretched. We cannot recognize looking as simply flat. On the other case, if it is capillary surface has no bendings at all. However, the stretches of capillary surface we can see because it is capillary surface completely determined by its shape. This is exactly our problem. Here in this here there is some capital variable x. What is the x? Usually say that x is some Lagrangian coordinates, but we have no initial data what is Lagrangian coordinates. In nonlinear elasticity theory, it's called reference frame, and capital X is some label of material, particle, some indefinite object, some reference frame, some variable. Really is not bad defined. Unfortunately, the stretching energy depends on the choice. It is not geometric invariant. It defined not by choice of our surface. It also depends on the parameterization. Therefore, we have, when we minimize this functional, we have to solve two problem variational. First problem, to minimize surface. When we find minimal surface, you have minimize the variable x, the parameterization of this surface. The first problem is simply plateau problem, which was proved by Friedrichs maybe near 100 years ago. But the second question is so-called variational problem, harmonic mapping, when you minimize Dirichlet integral for the mappings, we take the some domain into given surface. Therefore, it is a little bit complicated stuff. In our case, we can assume, because we consider periodic problem, we can assume that in reference frame also parameterization is periodic, but definitely the period should be other. It is not realistic that periods coincide in physical domain in this reference frame. I will assume that the periods, they are periodic with some latches gamma, and this gamma is determined by two vectors, which is, yes. Therefore, this vector determines periodic cell, and S has such representation where this is dual safe in the theory of crystal, which is well-known stuff. And takes the stretched energy is very simplest form. It is periodic, therefore I take integral only on the self-period. In this setting, both latches gamma, these two vectors, it is characterized by parameter t and alpha, and surface and cell, and parameterization of this surface, everything is unknown. It is integral part of the problem. Yes. It is a picture illustrates this is latches gamma, so it takes to sigma. It is periodic cell of the real physical surface. It is in domain of capital X, it is in physical domain. Okay? Therefore, I can write the total energy of the flow. It is the sum of this integral. At first glance, it is some quadratic functional, and at first glance, it is positive. There is nothing to minimize. But it is not so, because miraculously reduced kinetic energy, Kf, is not positive. Moreover, it is mostly negative. And more rigorous analysis in two-dimensional case shows that it is not quadratic functional, it has some cubic behavior or something like this. Therefore, the question becomes non-trivial. Okay. Variation, boundary condition. It is variation of problem. What is happening if we minimize this functional, or, for example, find the critical saddle point of this functional? When we make variation at this point, calculus of variation, assuming the solution is good, sufficiently smooth, we get the following formula. This is more or less trivial fact. Variation of capillarity of the stretching energy with respect to shape of variable, with respect to shape, normal variation, with respect to change of the surface, it is simply capillary force. It just gives some pressure. It should be minus pressure, more precisely, variation. This is non-trivial fact. It is Minkowitz, for example, yesterday was K2 prime plus K cube. H now it is multidimensional variation of K, it is Minkowitz. Instead, second derivative, it is the Laplacian, it is exactly H cube, but we have extra term, it is Gauss curvature. In two-dimensional case, Gauss curvature is simply 0. Yes, this identity was derived many years ago by Blaschke, but it was unnoticed, hidden in some of his books. But later it was rediscovered by Wilmer, and then it is now I just call it the Wilmer operator. Yes, okay. If you take together all this formula, we get the following boundary condition on the free surface, assuming the minimizer is smooth. First, it is exactly Bernoulli or some dynamic pressure condition, really. This is the bending energy terms, reflection for bending, which is responsible for bending. This is like capillary, it is terms induced by stretching energy. It is the kinetic energy, it is standard result for hydroelastic Bernoulli type law. Okay, and this is Neumann condition on the free surface. Everything is okay. Dynamics condition, kinematics condition. But I recall that I told that we have, when we find the variation of stretching energy, we have to take variation only not with respect to S, but only with respect to choice of the reference frame. The variation of the reference frame gives the following result, that this parameterization should satisfy this relation. This means that if parameterization satisfies these identities, it calls that our parameterization is conformal. It is the best parameterization. Therefore, when we minimize our functional, we get the dynamic condition, kinematic condition, and also we have choice of reference variables. It will be parametric. Okay. Now we have to answer 3 questions at the beginning. First, I stress that we consider with global theory, therefore we can assume that S is almost an arbitrary surface and G is almost an arbitrary domain. Therefore, the first 3 questions. First question, is magnitude of wave is bounded? Maybe yes, maybe not. Because we consider this global situation, it is possible. The second question, has the surface S self-intersections or overlapping? If yes, therefore our solution has no meaning because flow domain is simply not defined. And second question is not very visible, but surfaces should satisfy the peculiarity of our problem. Maybe most important stuff is that it is not geometric problem. We also have flow potential which is related to potential theory. For example, this integral is not defined on the an arbitrary surface. It should be satisfy some condition in theory of Sobolev space. As something that is good, it will be Lipschitz surface. From geometric point of view, it is mentioned if you have the second fundamental form of surface. The question is, are this quantity bounded or not? It is also, therefore, 3 questions. Self-intersections, boundedness of magnitude, and some regularity, minimum regularity of the surface, but we should discuss. Okay. In order to tackle to cope with all this difficulty, we need some short excursion in the geometry. It is interesting. Yes. First, no, I missed something. Yes, first, the first fundamental form, I formulated what is it. I simply recall definition from the university course of differential geometry or geometry. It is standard stuff, but only I have stressed what is conformal coordinates. The parameterization of the surface is conformal if you have these equations. In this case, usually people use the standard notations are used. These quantities like exponent of some f. It is important because logarithm f it is 5 very good equation in differential geometry, therefore it is standard notation. And then we can also introduce 2 vectors, 3 vectors. Each is normal, each is tangential vector, all 3 vectors are orthogonal, and then they can be defined some moving orthogonal frame on the surface. The method of orthogonal frames was introduced, considered by Cartan, and now it is very popular. It is special theory. What is orthogonal frame? What is an optimal, so-called Colombo orthogonal frames, and etc. Okay. Relation stretching energy. It is really some reformulation or some consequence or maybe some versions of the result of Yost in the variation of, in his book on the variational problem, two-dimensional variational problem. It can be formulated. Suppose you have some fixed surface, and suppose it is periodic, and then suppose there is one parameterization with some latches and with some parameterization such that the integral is bounded. It is enough. Then let us choose this forgiving surface to solve this problem of minimizing this functional. Then the minimum defines the conformal parameterization of S, and the lattice is not collapsed because it admits some estimate. It is more or less standard geometrical result. I simply stress that the optimal parameterization leads to the conformal coordinates, which is very nice. Now let us turn to the second quadratic form. It is formula from the university course. Don't pay too much attention because the coefficient of these quadratic forms depends on the parameterization. But eigenvalues or principal curvature, eigenvalues of this form, they are geometric invariant. They depend only on surface. Do not depend on parameterization. And I recall this definition for mean curvature and for norm. It is the Euclidean norm of this form. Euclidean norm of the matrix is the sum of squares of each eigenvalues. Okay, it is standard stuff. More interesting result about Willmore functional. Let us turn. I would like to say a few words about Willmore functional. Yes. It is conformal invariant in particular because all spheres are invariant with respect to inversions, rotations, and translations. It is obviously. Therefore, for any sphere, it is one constant, and this constant is 4 pi for any sphere. Spherical surface, well, of course not sphere, but spherical surface. 4 pi is a quant for the theory of Willmore functional. What does it mean? The first very remarkable result, very important, which we need. There is many interesting results, but the result which we need. It is the celebrated theorem by Li and Yao. It follows that if you have a closed surface and energy Willmore functional of this surface is strongly less than h pi, 2 quants, therefore we have only 1 quant and less, then the surface has no self-intersections. It is, yes, it is geometrical result. It is based on some simple idea, but there is some quantitative, there are some inequalities which give some more or less analytic explanation of this. And next is only for curiosity, the variational problem for this functional, for closed surface for fixed topological type, like genus was considered first by Simon. He proves the existence of minimizer amount of closed smooth torus. And then for further result, I refer to this paper and also many papers of these authors that contains a lot of informatics. new result, a lot of information, new result, and references. Okay. Next, about minimal smoothness of this surface, it is not so good. It is really in geometry, it is question about so-called Lipschitz parametrization. Is the surface is continuous, Lipschitz continuous? First, this result of this time was proved thorough. Next, it was repeated by Müller and Schwerak. They was not so good, but much later, Helene in his book developed a method using the method of moving frame, developed more better theory, combining this Helene approach and some result of the best estimates in so-called geometric event inequality, we arrived to the following statement. Assume that we have conformal parametrization of some periodic surface. I recall this notation. Assume that it is, in fact, it is sufficient that it is simply bounded, it is not infinity. Assume that this energy is less than 16 PO3. It is not optimal estimate. But then, the most important is here. The coefficients of the first fundamental form are uniformly bounded. Uniformly bounded. In fact, this constant is near 1 over 2 pi, as was proved by Topping. Next, they have bounded Sobolev norms, and next they have bounded these norms. Therefore, it is in some sense the surface of class W22, Sobolev class, and this is the most important part. It follows from this, if it defines the geodesic distance on the surface between 2 points, like this minima, then we have this. In other case, this conformal parametrization defines Lipschitz coordinates mappings on the surface, and this means the surface is a minimum Lipschitz. Okay? Now about overlapping, the consequence of Yau result. Unfortunately, Yau result is related to closed surface in the closed surface in Euclidean space. Our period sigma is not a closed geometrical surface. It is topological torus because we can identify, but it is topological. It is not embedded to some Euclidean space. Therefore, we have to organize such an embedding. The simplest way, I can find nothing better to put this sigma, this torus, into 5-dimensional surface, which can be given such parametrization. Y5, it is easy to put surface manifold in the space of high dimension. It is difficult to put manifold in the space of small dimension. It is well known. Therefore, 5, I can also take 7 or something like this. This parameterization 15 defines the closed torus in 5-dimensional space. Now, it is smooth, it is real torus. It's 2-dimensional torus, but in multi-dimensional space. It is mapping has some remarkable property, but most important that curvature, real curvature of this now real torus is equal to the bending energy plus 2 pi square. 2 pi square, it is the minimal Willmore functional for torus. There is famous Willmore problem, which was solved, or we believe that it was solved only a few years ago. It was Stanford the case, to find the minimum, to prove that 2 pi square is the minimum Willmore functional for amount toric. Therefore, it is exactly this quantity. Now it should be less than 2 quants. 2 quants at HP. Therefore, we have this restriction on the band count. Okay? Therefore, we have so bounds. The first bound prevents self-intersection, which is good. The next bound, sorry, where is it? The next, yeah, no, the second bound guarantees that surface is Lipschitz, also good. Therefore, if this bending energy is not so high, the surface is not so bad. Okay, it is definitely not optimal. I think that 3 maybe we can, without 3 is not needed, but it is very difficult so-called Hellenic problem. It is greater than this, therefore we can restrict our bending energy by this quantity. Now I have to organize the variation to formulate the variation of problem in this setting, assuming that bending energy is bounded by this quantity, if it is a case. Therefore, I have to reformulate initial problem, roughly speaking, in a very bad way to damage. Let us consider 2 functions. Psi dh is function on one real variable, such they should be monotone and they should be tends to infinity as when s tends to this critical value, and then this doesn't matter any constant. Really, we don't need this. And replace our energy by the following. It looks like that I do the horrible things. I replace real energy by some nonlinear terms. But really, if we calculate variation, this simply means one simple thing. I assume the constants Cm and Cb are known and should be defined along with solution. It is not good, but it is not big catastrophe. I simply, this is assumption that these 2 parameters are unknown. It looks like strange, but if you take the variation of this function, you have seen this function, these 2 functions influence variation like some constant derivative of psi. Yes, therefore it is now you have very good things, because now the bending energy is less than critical value, 16 pi over 3, and this functional, we can check that this functional now is, as we say, Law-weakly continuous in some sense. Therefore, we can formulate the following result. Let us consider the set of all Lipschitz periodic surfaces. It is not necessary, but I try to avoid the shift. Solution is invariant with the vertical shift of the translation of the free boundary in order to limit. It is not restriction, really, it is something. Then I try to find the minimizer for along these quantities, and this is the surface which really gives the minimum to this function. Therefore, the minimizer exists, it's a Lipschitz surface. The interesting question, is it trivial? Maybe result is flat. So I make a lot of works, but the result will be trivial against flat surface. I don't know what minimizer is. Now, if these functions are not so big, this means that coefficients Cm and Cb, roughly speaking, the elastic part of energy is relatively small with respect to hydrodynamic path. Then the limit is not flat. It is easy to check, because for flat surface our function is simply 1. If I take some test surface like graph of this very simple function and calculate this function, you have this. Here minus, it is kinetic energy. Here minus. I say that kinetic energy, reduced kinetic energy is not well defined. And plus it is easy to check that for every lambda I can find n such that it is negative, then if these quantities will be small, then for such Mn, this will be less than 1, therefore our result is not trivial, not flat. Okay, now I have no time, I skip the proof. The next result, it is very nice picture, but I have no time to explain what is it. Okay, I will simply formulate the result. This surface is smooth, it is infinitely differentiable, it is the most difficult part of the proof. It is based on the so-called hole filling method. And this is the main difficulty this method applying for in geometry. But I stress that it is new class of the problem, because we have minimized not geometric quantities, but also Dirichlet integral over domain. This class of mathematical problem is new, and therefore methods should be defined. It is difficult. As usually, it is the most difficult part of the proof. For example, for plateau problem, the famous Algren theorem that any critical points of the plateau problem, not minimizer but critical points, is smooth. It is not proved yet, and it is formulated, assuming that it is correct. And some people estimate proof like 300 pages. It is not finished, the work is continue. The other people estimate like 700 pages, length of proof. Therefore, these questions, but for variational problem, to be honest, it is easy. But if you have some saddle points and something, it becomes extremely difficult, extremely difficult. For example, Hilley writes his book in order to prove some results of this kind for harmonic mappings. Some remarks and generalization. I spent a few minutes in the end. First, it is impossible that velocity that we have such latches of period and horizontal velocity. Of course, no. You can take any self of period and physical domains and any velocity. It is theorem. More interesting remark, can we replace bending energy by simply capillary energy, replace this function or by this? It is very nice because it is geometric function, no reference frame, no, okay? I think yes, but it is possible. More difficult question, can we skip this bending and stretching energy at all? Yesterday there was no stretching energy, no talks. This question is difficult, because in this question I cannot estimate the magnitude of wave. Okay, it is technical, okay, of course. This question is very important. Suppose I take Cm and Cb elastic constant take to 0. At the limit, I expect that at the limit, even in maybe in two-dimensional case, I can expect that at the limit I have got Stokes waves. No, for Stokes waves, minimum is minus infinity. It is cubic function. Therefore, the question of saddle points. And the last question, it is unsolved. And the last question, I only mention it, is very interesting. We are in moving frame. Suppose we are real physical frame. It was noted by John that we can parameterize two-wave propagation. Really, one propagation is reference frame velocity wave, and the other velocity propagation in physical plane. We don't take account in our considerations that the shell has a mass, but each has a mass. Then analysis shows that the stretching energy may be damaged and it should be replaced by this function. If V is large, supersonic, this form is not positive definite. It creates a lot of problems. This question is not investigated, but the question about true speed of propagation, it is. Okay, I finished. Let me stop at this point. Thank you very much for attention.
Any questions?
As far as I understood, you proved that if the bending energy is not so large, the surface, the wave more or less smooth the existing wave or the surface.
It is analytic. It is very smooth.
Does it mean that Stokes wave is forbidden with angles at their top?
The answer is an interesting question. Okay, I understood. It is will more functional. It has singularity, but others. Roughly speaking, I say there is quant for P. If the bending energy is greater than HP, then singularity, very special kind, may be.
Maybe, but not.
No, this question for in geometry was investigated by Mikhail Kruger. Quant of each singularity is for P. Okay.
Thank you.
How do you define kinetic energy that it's negative? It should be special definition because usually it's just positive by definition.
It is really not kinetic energy, it is renormalized kinetic energy. Therefore, I have to integrate this. I have to write kinetic energy, then integrate the linear part by part, reduce to surface integral, and remove some constant, and after this it will be not positive. Therefore, I withdraw some constant from kinetic energy. Therefore, it changed sign.
So if we say kind of kinetic energy, it would be less confusing.
No, renormalized kinetic energy, yes. Like joint mass or something like this.
Very short, very short. So actually you derived, you showed the inequality for deformation of the surface. And then, if we have numerical solutions shown, which were shown yesterday, so we can calculate that integral of that big A, and we can check or say something about that inequality.
Okay. I think real waves has no such large magnitude or such large
Numerical, it's
curvature. Numerically, the way we look in arbitrary waves, but really real waves are not so steepest or something like this. I think that mostly they should satisfy. I don't know, because quant for pi, it is very important thing.
Okay, we better finish there. Thank you again, Pavel. Mariana,